Welcome to the last lecture in Module 3 on finite difference. So, concluding lecture on the computer implementation of finite difference method for 1D heat conduction problems. So, let us have a recap of what we finished in the previous lecture. We discussed a bit more about data structures and their implementation in a C++ code, and we also finished implementing the major modules in a C++ program for solution of one-dimensional problem using developer C++ IDE. Now, in this lecture we would try to finish the remaining modules, basically sub-modules which require the implementation of boundary condition. So, this is our last lecture in the series on computer implementation of finite difference method for steady state heat conduction problems. So, we will focus on the pseudocode and C++ implementation for incorporation of boundary conditions for both standard as well as cell-centered finite difference formulations, and then we will complete our code. That code would be complete in all respects. We will compile it together and test for one or two sample problems, and we would compare the numerical results for a test problem obtained with the standard and cell-centered finite difference formulation. So, we have already done our code design and we had implemented our input module. We had implemented the outline of the module systematics for generation of the finite difference discrete system, and we need to complete the incorporation of boundary conditions in this module, and then we said we are going to just call an already available module TDMA based function to solve our system of equations. Okay, we have already seen in the previous lecture the pseudocode for input and system matrix module. Now, we are going to work on implementation of boundary conditions. We will have a look at the pseudocode for that, and we would implement it in the code for both the cases, that is BCS normal, that would stand for the standard formulation, and the cell-centered formulation. Okay, now, before we go for implementation, let us first have a look at what modifications we need to incorporate in our code for implementation of boundary conditions. So, implementation of boundary conditions. Now, the end result would be the modification in the discrete equation. We had our generic discrete equation, for a node I. This was given as AP Ti plus AW T of I minus 1 plus AE T of I plus 1 is equal to BI for a generic node I. P stands for the current node, E stands for its distant neighbor, that I plus 1, and W stands for its left neighbor or a western neighbor. Now, what do we mean by boundary condition? That we have to now modify the boundary condition would be specified at the end of the domain. So, we need to modify the nodes, the computational nodes which are in the vicinity, obtain a modified discrete equation. So, we will have a modified discrete equation for boundary nodes. So, let us take the two cases separately. Like first, let us deal with our standard finite difference grid, wherein we have the nodes aligned with the boundary. So, the standard finite difference formulation. I will put the pseudocode only for 1 or 2 cases here. Let us say the 2 possibilities and we have to deal both the possibilities separately. Okay, so let us take the case when, let us call it case 1 or case A, left boundary. By left boundary we mean we have to obtain a discrete equation or modified equation for node 1. Node 1, node 2, node 3 and so on. This is the interior of the domain. Now depending on the boundary conditions which is specified at node 1, we will have a different set of equations or different form of equation for this particular node. So let us have our BC type is equal to 0, that is we have T1 is equal to TB. Now if this is given, of course this becomes our discrete equation, okay, and if we compare with the standard or generic discrete equation which we have derived for all the nodes, or we have would have computed in our code earlier for all the nodes, okay. So on comparison what we say, that this coefficient now I would write in a pseudocode format so that we can translate it easily into a code. So basically all that we need to do is set the coefficient AP of the node 1 as 1, AW and AE should be set to 0 and B1 should be set to TB. That is all we need to do. So at AP1 this is set to 1.0, this left arrow, this is a standard notation in computer programming that assign 1.0 to AP1, AE1 is equal to AW1, and these would be assigned 0 values. Our B1 would be assigned the boundary conditions specified at this node TB, T subscript B. So now this is one particular case or one condition. The second condition could be we have got the flux is specified. So flux conditions, we have to be careful the way we define the flux and take care of the direction of the normal. Normal is now directed in negative x direction. So we have got a flux definition, Q is given by minus K del T by del N or dt by dN. Now here N is aligned in negative x direction, so we would get in terms of x this becomes K times dt by dx at point 1. Now we have got this derivative here and it has to be approximated, and we have got no choice other than using a forward difference scheme. So we are going to approximate this as K times T2 minus T1 divided by delta x. So now let us take two subcases. The first subcase of BC type 1, BC type is equal to 1, which stands for flux specification, that is Neumann boundary condition Q at x is equal to, or I is equal to 1, this Q is given as QB. So if you set this value, to our finite difference approximation, we get k times T2 minus T1 divided by delta x is equal to QB, and this gives us our standard equation T1 minus T2 is equal to minus k times QB divided by delta x. So, a pseudocode for modification is AP of 1, we set it as 1.0, AW at node 1 that is 0.0, and AE at node 1, this will be set as minus 1.0, B for this node 1 that is minus k into QB divided by Tx. Okay. Now, the next possibility is the last one is our convective boundary condition, which stands for BC type in our code. We have set that as 2 is our integer flag. So, this stands for convective BC. Okay. Q is equal to H into T minus TA at node 1. So, that simply means our k times T2 minus T1 divided by delta x is equal to H times T1 minus TA. If we rearrange it, we get T2 minus T1 is equal to H delta x by k times T1 minus H delta x by k times TA, that is 1 plus H delta x by k times T1 minus T2 is equal to H delta x by k times TA. So, pseudocode that is AP of 1, this has to be set a value which is the coefficient of AP now in this T1 in this equation. So, it is 1 plus H into dx divided by k. This is the value which you assign to AP of 1. E of 1 would be assigned a value minus 1.0, AW of 1 we should set as 0, and B of 1, which includes now the effect of convective boundary condition, this would be set as H into dx into TA divided by k. So, these are the lines of code which we need to incorporate in our program. So, now let us get back to our program and see the actual implementation. That is incorporation of boundary conditions on a standard finite difference grid, modify the entries of system matrix A and RHS vector B for boundary nodes. So we have called this routine as get BC normal. Normal stands for standard finite difference formulation. Our inputs grid, matrix and boundary condition type. And what we have discussed so far is our left incorporation of boundary conditions at left end. So let us introduce a local variable type is equal to BCS0 dot type and Dirichlet BC. So we can set this, if we assume the Dirichlet BC to be present anywhere, we have seen that AP1 that is set to 1.0, the rest of the coefficients AW and AE at node 1 they are set to 0.0 and the source term that becomes our specified temperature value. So that is what we saw in our pseudocode. Now if we have, if type is equal to 1, that is we have got Neumann BC, then we need to change AW we have already set to 0, so we need to change AE and B. AP we have seen in this case remains as 1.0, so we don't need to write a separate line in this block. So we just change AE, so m dot AE1 is equal to minus 1.0 and m dot B1 that is given by minus QB dx by k. So we have put in the access specifiers at BCS0 dot QB, that will give us the specified heat flux at the left node, grid dot dx that gives us grid spacing and grid dot k that is has stored the thermal conductivity. Next, when we come to convective boundary conditions, we need to change AE, AP and B, these three. AW we have already set to 0.0, so we do not need to worry in this block. Let us define a local variable h dx k which includes h into dx by k. So h dx k stands for BCS0 dot h. Remember this 0 index is being used for boundary condition at the left node into grid dot dx divided by grid dot k, and AE m dot AE1 that is the coefficient corresponding to the eastern neighbor, that becomes minus 1.0, coefficient corresponding to the current node, that is 1.0 plus h dx k, and our boundary condition which now influences our source term, that becomes m dot B1 is equal to h dx k into BCS0 dot dA. So whatever pseudocode which we have written, we have now incorporated that in our code, boundary conditions for the left node. We need to do the similar exercise and we ought to obtain the pseudocode expression for boundary conditions at the right node. So we are still with standard finite difference formulation. So BC is at right end node. So let us draw a sample grid. This is our grid point and its index would be n plus 1 if your number of division is n. This left node will have an index of n and so on. Boundary conditions would be specified here. So let us have three cases. The first one is our BC type is equal to 0, we simply say that Tn plus 1 is specified as given boundary temperature. So if this were the case, all that we need to do is set the corresponding entry. So let us choose a simpler term, let us call it, let us define that nx is equal to n plus 1. So AP of nx, set its value to be 1.0, AW nx and AE nx they will be both provided with 0 value, and our right hand side vector is b and x, we need to store in it the specified temperature value. Now the next one, the flux type boundary conditions or flux type basis. So now in this case we need to come up with an approximation for the flux term itself, which will involve a derivative. So now let us say q is equal to minus k dt by dn. Now in this case our vector n is aligned with positive x direction, so dt by dn and dt by dx, they would have the same meaning or they would be identical. So this minus k dt by dx, and this now dt by dx we have to approximate it using an one sided difference. So we will use backward difference approximation using the values at node n plus 1 and node n. So this will be approximated by Tn plus 1 minus Tn divided by delta x. So now let us take two sub cases. The first one is Neumann BC, which corresponds to our integer flag BC type is equal to 1. We have q is equal to qb. So this simply tells us that k times Tn plus 1 minus Tn divided by delta x, this is equal to minus qb, or we can write this as minus Tn plus T of n plus 1 is equal to minus qb delta x divided by k. So if you compare with what we had obtained, the expression for the left hand, the expression is fairly similar, only the indices have changed. So a pseudocode now, which we need to incorporate in our function, our AW nx, this is, or this should be set with the value of minus 1.0 APNX, this should be set a value of 1.0, and BNX, this should be assigned a value minus QB into delta x divided by k. Now this next case, that is your convective boundary condition. It says q is equal to h times t minus Ta. So it says k times t of n plus 1 minus Tn divided by delta x is equal to minus h times Tn plus 1 minus Ta. Remember, in our writing we have just transposed the signs. So alternatively we can rearrange it as Tn minus Tn plus T of n plus 1 is equal to minus h delta x by k into T of n plus 1 minus Ta. Rearrange it further to put it in standard form. So, minus Tn plus 1 plus h delta x by k times T of n plus 1 is equal to h delta x by k times Ta. So, compare this expression with our standard discrete equation for this node, and then we can say that what we need to modify, that is AP of Nx. Remember this Nx we have introduced as a sorted notation for n index n plus 1. So, remember that Nx stands for n plus 1. So, AP Nx should be assigned a value 1.0 plus h into dx divided by k. AW Nx should be assigned a value of minus 1.0, and AENx this will be set to 0.0, and our load vector that element of B at this point grid Nx, this should be assigned a value h into dx into Ti divided by k. So, now this completes our pseudocode. These 4 lines are the ones which we need to directly put in our code to take care of the incorporation or the effect of convective boundary condition. So, let us get back to our code. So, incorporation of BCs at right end. So, type is equal to BCS1. Now, this argument of 1 stands for the boundary condition at right end. So, get the type of the boundary condition, and as we said, we are going to now introduce a local integer int Nx is equal to grid dot n nodes. So, Nx is actually this stands for the value capital N plus 1, where n is the number of divisions. Now, let us put the Dirichlet BC, okay, that is the simplest one, and let us assume that were a default BC. So, in that case our m dot APNx, that is provided with the value 1, remaining coefficients was set to 0, and m dot BNx is set to BCS1 dot TB. Now, change for other 2 types of boundary conditions. If type is equal to 1, that is our Neumann BC. Now, in this case for the Neumann BC we have already seen our pseudocode that APNx that should be set to 1, that we have already done. So, we need to just check the values of AWNx. So, m dot AWNx is equal to minus 1.0, and next m dot BNx, which includes the effect of QB. So, minus BCS subscript 1 dot QB into grid dot dx divided by grid dot k. Now, in case of we have got convective boundary conditions, so we need to change that again AW and AP and B. So, let us define a shorthand notation variable h dxk, which stands for h into dx divided by k, and our access specifiers for h would be BCS subscript 1 dot h into grid dot dx to grid divided by grid dot k. So, m dot AW for the node Nx is minus 1.0, m dot APNx that becomes 1.0 plus h dxk, and m dot BNx is equal to h dxk into BCS 1 dot Ta. So, now we have finished our coding part for the incorporation of boundary conditions with standard grid, that is our vertex centered grid. Similar exercise we can repeat for the cell centered finite difference grid. I will not do the complete derivation for the pseudocode, that I would leave as an exercise, But a few salient points I would just like to mention which you should remember for cell centered grid. For cell centered finite difference formulation, please remember at two ends, at left end, at both ends we are going to introduce what we call ghost points. Remember, the computational nodes are in the center of the cell, and this is our problem domain, this is our boundary, left boundary. The boundary conditions are specified here. So, we will introduce a ghost node of 0 and temperature at boundary, let us call that as T of B. Now, Tb would be approximated as an average of the temperature at point grid node 1 and or ghost node 0. So, Tb would be given as T1 plus T0 divided by 2, and we can easily use central difference approximation for derivative. So, dt by dx at, let us call it as x is equal to xa, our left end, this would be approximated as T1 minus T0 divided by delta x. So, you need to just take care of these two definitions in deriving the expressions and the corresponding pseudocode for incorporation of either Dirichlet boundary condition or Neumann or convective boundary condition. Similarly, at right end, let us redraw our domain. So, we are at now x is equal to xb, this is our computational node with the index n plus 1th node becomes now our ghost node. Now, what would be the temperature values at the boundary T at x is equal to xb? This has to be approximated as Tn plus T of n plus 1 divided by 2. Use CDS for derivative, and all that it means is dt by dx at x is equal to xb. This can be approximated as Tn plus 1 minus Tn divided by grid spacing delta x. So, what we will do, our general procedure would be for obtaining expression or expressions for boundary nodes would be substitute for the value of T at ghost node that is T0 at left end and Tn plus 1 at right end, obtained from specified BCs, specified boundary condition, into standard discrete equation AP Ti plus AW Ti plus 1, sorry, Ti minus 1 plus AE T of I plus 1 is equal to Bi. Okay. So, at one end of Ti minus 1, like left end Ti minus 1 would become T0. So, eliminate, we have to get the expression for T0 from either Tb is equal to T1 plus T0 by 2 if Dirichlet boundary condition were specified, or from the flux specification solve for T0, substitute that in this equation and get a modified discrete equation for that node. So, I would leave the completion of this task as an exercise. So, obtain final expressions for incorporation of bases and put them, and rather implement them in our C++ code. Remember, this C++ code would be available to you, what we are looking right now in the lecture, on NPTEL site, so you can download it and do your modifications. I will just give you a brief look at the skeleton of what I have done, that BC centered, and this is exactly in the same way, is a bit more elaborate compared to the standard format, but the remaining code is exactly similar to what we had looked in detail for standard boundary condition. Now, this completes our code, okay, and you can compile it and run it and test it for a certain set of problems. Now, let us do a sample run. And if you perform a sample run, I would straightway give you some results for two sample test problems. So, the first test problem is the steady state heat conduction in a slab of width 0.5 with temperature dependent heat generation, that is Q is 1273 minus T watt per meter cube, and the left end of the slab is maintained at T is equal to 373 Kelvin. Right end of the slab is being heated by a heater for which the heat flux is 1 kilowatt per meter square, and thermal conductivity is constant, it can be taken as K is equal to 1. So, just input all these values in our code, and this is what do we get for the standard grid by taking 5 grid divisions. Okay. The temperature values range from 497 to 928. Exact solution for this problem can be easily obtained, that is again left as an exercise to you. It's all decoded as a part of the code, a simple function is available which gives the exact solution, and our output routines also computes the percentage error based on the exact solution. So, for this choice of the grid, percentage error ranges from 0.34 to 9.94. Now, you can observe one thing, that error increases from node 1 to node 5, and the reason is close to this node, in fact there are nodes 2, 3, 4, 5, 6, node 0 which is close to this x is equal to 0.1, we had temperature specified. So, at this end errors are less, but at the right end where we had approximated our flux by a first order backward difference scheme, we get fairly large value of error. Now, FDM results with a cell centered grid. Now, the grid points are at in the middle of the cell, 0.05, 0.15, 0.25 and so on. Okay. So, now you can easily say that errors are very small, they are much smaller compared to the solutions which we have obtained with the standard finite difference grid, and specifically prominent is this last figure, that close to the right boundary where the flux was specified, now we get error less than 0.1%, and the reason for this accuracy is that at the right end flux has been approximated by a second order accurate central difference scheme. It ends the set of results which you can obtain. You can try and run the code for this particular test case, a slab of width 1 meter with constant heat generation. This is a test case for convective boundary condition. The left end of the slab is maintained at T is equal to 373 degrees, and the right end is losing heat by convection to ambient at 273 Kelvin. The heat generation is constant 500 watt per meter cube, and the thermal conductivity can be taken as 1. The convective heat transfer coefficient, let us say we have taken 30, and this is the result obtained with our standard grid. So now this is where we are now going to put our end to our discussions on finite difference, but before we close, I would like to leave certain exercises for you. Now these exercises pertain to writing an actual implementation. So let me call them as coding exercises. Number first, extend as 1D code to a 2D code. So design philosophy you can follow the same the way we have discussed, but now the things will change. The grid is, the data structures would change, the solvers would change, and you can use or you can implement an iterative solver for solution of 2D steady state heat conduction. A simple exercise could be to modify this code to solve 1D steady state advection diffusion problems. Now some of the solvers we will discuss in the next module, which you can make use of. Now just broad references for what we have discussed. You can get lot more material, many more finite difference algorithms, and the approximation schemes in these two books, particularly Chung's book Computational Fluid Dynamics. It is a compendium of a huge collection of finite difference approximations together with finite volume and finite element methods for CFD applications, and similar more readable account, a much shorter account you can find in Fertzigers and Perick's book. You can also try another book on CFD, Introduction to Computational Fluid Dynamics by John D. Anderson, which is a lot simpler to read than either of these two books. So for now, this way we would put a full stop to our discussions on finite difference method, and in the next module we will focus on the solution of discrete algebraic systems.